welcome everyone. Have a seat. We have refreshments in the back if you'd like. So people online, feel free to ask a question in the chat box. Samir, is that right?
Yes.
Yes, and we will hopefully have a chance to answer everyone's questions, yours as well. So without further ado, please join me in welcoming Hank Greeley.
Thank you, Rob. So I have all the things that Rob said, and I'm 15 minutes late. Or with being 10 to 15 minutes late for a dinner party, it's kind of about right. You don't want to be doing on time. But for a speaking engagement, I'm really embarrassed that I'm late. I will say, having lived now in the Bay Area for 34 years, it's clear that we're about due for a recession. Because every time the traffic gets completely unbearable, the economy tanks. And then the traffic's good for another 3 or 4 years, and then it begins to get worse and worse. I'd say, based on today, we're due for a recession next week, or sometime soon. Thanks, Rob, for having me out here. What I want to talk about today is some thoughts that come from the next book that I'm writing called Playing with Life. Specifically, I want to talk about the use of CRISPR in non-humans. The use of CRISPR in humans is much more au courant right now. But I want to talk about it in non-humans. But I want to start by asking some questions. I'm sure most of you have heard of the HeLa cell line. The cell line derived around 1950 from the cells of a cervical cancer of a patient named Henrietta Lacks. There's a wonderful book about that that I highly recommend by Rebecca Smoot. But what I'm going to focus on right for a second is there are approximately somewhere between 20 and 100 tons of HeLa cell lines around the world. It is the weed of cell lines. About every decade, somebody comes up with a new paper saying, here's a list of the following 80 papers that have to be disregarded because people said they were using lung cell lines or kidney cell lines or heart cell lines, and it was all HeLa, because HeLa is an extremely invasive cell line. There's more HeLa out there by weight than there are probably southern white rhinoceroses. The HeLa cell line started out as the DNA from Henrietta Lacks. And then it became the DNA from a cervical tumor. And tumor DNA is our DNA, but it's mutated in various ways that turns it malignant. And then over the years, it changed more and more. One of my Stanford colleagues a few years ago sequenced one of the more common versions the HeLa cell line. All of us in this room have approximately 6.4 billion base pairs of DNA, 2 different DNA sequences, each 3.2 billion base pairs, more or less, one from our mom, one from our dad. The HeLa cell line has 9 billion base pairs of DNA. Almost certainly, everybody in this room, except the dog, has 46 chromosomes. I actually don't know how many chromosomes a dog has. We all have 46 chromosomes. The HeLa cell line has somewhere between 75 and 85 chromosomes. Some of them are our normal human chromosomes. It has 5 copies of some chromosomes. Some of them are bits and pieces of one chromosome mashed together with another chromosome or 2. And yet it is very non-human, and yet it's very hardy, prolific, and large. What is the HeLa cell line? What is it? Is it a human single-celled species of thing? That's one question. Different question. A couple of years ago, some people published in Science magazine an article about something they had made. They took a piece of very thin, do I need a microphone?
Yeah, I want people online.
Okay.
And he just a little better.
Sure. If they're in New York City, my voice is big enough to fill this room, probably not to get across the line. I could try, but it would be a mistake. Okay. So they took a framework, flexible framework of very thin gold wire, about the size of what used to be a $50. I don't know whether they still make $50, but a little bigger than a quarter. Okay. Hinged it in the middle so that it would go up and down. Covered it with a thin, transparent plastic coating. And on that coating, they put rat heart muscle cells. Not just any rat heart muscle cells, but rat heart muscle cells that have been treated through a process called optogenetics in a way that meant if you shone a light with the right frequency on them, they would fire. And being muscle cells, when they fire, they contract. They took these things and they put them into a little aquarium tank that had oxygen and glucose in it, which made the rat heart muscle cells very happy. And then they'd shine the light on it. And when the light shone on it, the cells contract. It goes like that. When it's like that, it doesn't see the light anymore. The cells relax. It goes like that. It sees the light. They swam those things around the tank. Some people were calling it a ray bot or a manta ray. It's like a little manta ray. Is that a living organism with a metal prosthesis? Is it a machine that has a biological component? What is that? And last one, this April, a Yale professor named Nanad Sistan, doing work that had originally started as a way to be able, boy, my voice has just gotten serious. Well, I feel like I should be a radio announcer. Always had a good radio voice and an equally good radio face. Nanad Sistan was trying to come up with a way to preserve human brains well enough so that you could actually do very, very detailed census of the 89 billion neurons in our brains and the roughly 900 billion non-neuron cells in our brains. Not only see which cell types were where, but what they connected to, where they were, where the synapses were forming. You can preserve a brain kind of in formaldehyde or formalin, and it feels kind of like a basketball. You know, you see some gross stuff, but after a few minutes of death, a brain begins to turn to mush. So he was trying to figure out a better way to preserve brains. And the experiment he did, which was reported in Nature, and the cover story in Nature in April of this year, was not with human brains, thank goodness, pig brains. He's at Yale, he's in New Haven, goes to the slaughterhouse. The slaughterhouse agrees to sell him pig heads at a good price because the alternative uses for pig heads are not all that valuable. Sausage and a few other things, dog food. Took the pig heads, the slaughterhouse decapitated the pigs, took the heads and hung them and drained them for 4 hours, gave them to Sistan, but then hooked them up to a pump, a process, a machine he calls Brain X. And the pump contained a perfusate, a solution that would go through the brain. It didn't have any cells in it, so it wasn't blood. It was clear perfusate, but it contained glucose, sugar. It contained hemoglobin, so it could carry oxygen in and take CO2 out. It contained a number of other chemicals that he thought would help. Conventional wisdom is, with a mammalian brain, within about 10 to 12 minutes of losing all oxygen, cells die and they don't come back. Every once in a while in the literature, you'll see something usually involving a young child who's drowned in a very cold lake, who can come back after about 25 or 30 minutes. But those are exceptional. Pump this into the pig brains. Pig brains kind of came back. The cells started firing. They got good circulation. They did patch clamping and saw that a process to watch the firing of the cells. They could see that cells were firing against each other. They were taking in oxygen and glucose. They were giving off carbon dioxide and other things. He did not, happily, hit a EEG. So, as he put it, the brain cells were alive, but the brain wasn't alive. The EEG would show that there were patterns of firing, consistent patterns of firing. But, and he doesn't push this very hard, one of the reasons he didn't get an EEG is he put something into the perfusate to discourage neuronal firing, to discourage getting an EEG. One reason for that, the one that he says most loudly, is there is some evidence that too much excitation of neurons in low oxygen conditions is what causes them to die. So he was trying to keep them from firing. But another reason was he didn't want to get an EEG. Because if he got an EEG with these pig brains that were dead for 4 hours, what's that mean about that pig brain? What's that mean about that pig? What's that? Is that a pig brain? Is that a pig that's lost its body? And if we did that with Rob, is that Rob's brain or is that Rob? Does somebody have to get a divorce, or is the marriage over? Does the estate get distributed? Can he vote? In Chicago, you can always vote as a dead person, but I'm not sure about New York.
Could I be president?
Oh, Rob. Not going there. So you'll notice none of my three examples says anything about CRISPR. The broader project is about ways in which we are going to be able to, are already able to play with life, to change life around in ways that it's not entirely unique. We've played with life for a long time. That little dog, 20,000 years ago, that was a wolf. I often wondered what wolves think about little dogs, other than thinking that they'd be a nice appetizer. But we did that. We turned a wolf into either that wonderful thing or that silly little fur ball, depending on your perspective. We change life all the time, but we've now got tools to change life in a variety of ways. The biggest of those, and that involves things like hybrids. I've got a colleague at Stanford who's making cells that have half of their chromosomes from humans and half of their chromosomes from chimps. He's not trying to turn that into a thing, into a living organism. He just wants to study the cells to see which genes work how. Hybrids, chimeras, things that are mainly from one species but have chunks of, say, brain cells from another species. Researchers are doing that. They're making things that are part machine, part animal, cyborgs, cell bots, a variety of different things. We're doing all sorts of stuff. But the thing we are doing most that looks easiest and I think is going to have the most effect in the world is CRISPR. So what I want to do, after that way too long introduction, is to tell you just a little bit, about CRISPR and about a particularly nice trick with CRISPR called gene drive. Then I want to talk about how we are likely to use CRISPR and gene drive in non-human organisms. I'll say a little bit about the animals that are us humans, but I mainly want to focus on non-human organisms. Then I want to say a little bit about what we might want to think about how to regulate it. And last, and to me kind of hardest, I want to raise the question, how should we even think about this kind of ability to radically transform the biosphere in new ways? So let me start with CRISPR. My guess is you've all heard about CRISPR. Clustered, regularly interspaced, short palindromic repeats. I am eternally grateful to Francisco Mojica, who was the Spaniard who, along with a Dutch scientist, first named this, that he picked a name that gave a nice, easy acronym. He's Spanish. I don't know whether he realized that it produced this great English acronym, but not only does it sound cool, but you can make it into a verb easily. You CRISPR something, you CRISPRed something, you're CRISPRing. In general, I'm not keen on acronyms, but CRISPR is a great acronym. It is also an amazing discovery. Now, who exactly discovered CRISPR is costing literally scores of millions of dollars. My graduates, Stanford Law graduates, maybe even some Columbia Law graduates who do patent law are making a mint off the question of who gets what patents on CRISPR. The truth is, CRISPR was invented about 3.5 billion years ago by bacteria. No human invented CRISPR. Personally, I think probably the best claim is that of Jennifer Edelman across the bay in Berkeley, and her collaborator, Emmanuel Charpentier. What they did is realize, building on the work of lots of people, including Mojica and others, who just thought, this is a really interesting thing in natural history. What are these cells doing? What's going on here? she realized we could turn this into a tool. So CRISPR for bacteria is an immune system. We all got immune systems. They're really complicated. We got white cells and macrophages and all sorts of stuff. Bacteria have only one cell. They don't have that kind of immune system. But bacteria, like us, all create viruses. For bacteria, the viruses have a funky name of phage with a PH. They get attacked by bacteria, and CRISPR is a way for them to fight back. With CRISPR, the bacterium will recognize some of the viral DNA or RNA, and then let loose a thingy, a construct, that is in part RNA, in part protein, that will cut that viral nucleic acid chain off. And what Charpentier and Gallagher realized is we can do this in the lab too, and use it to cut up DNA, and that would be useful. So the best analogy for CRISPR, everybody uses it. I wish I could come up with something novel, but how many of you have used word processors? Everybody, right? You use the cut and replace kind of function. Words cut and replace. That's CRISPR. You tell CRISPR, by giving it a chunk of RNA, maybe 20, 40 base pairs long, look for this sequence. We're going to put your set your loose on some DNA, look for that sequence. And it turns out, kind of surprisingly, that of the 6.4 billion base pairs of DNA that we all have, if you've got a 20-mer, 20 letters of it, that may only occur in one particular spot in your DNA. Or one or two, and if you get to 30, almost certainly, unless it's one of the repetitive sequences, almost certainly only one spot. And we can say, aha, that's on the short side of chromosome 8 at the 3.2 level in terms of breaks. And furthermore, this is part of what codes for globin gene. And it's the globin gene that when it's got one little twist, when it's got, I think it's an A instead of a T or a T instead of an A, it makes globin that makes funky red blood cells that give people who only have that version sickle cell disease. One letter change. So what you could do is tell CRISPR, find these 20 base pairs that include that thing that has the one wrong letter. Find it. And then an associated protein, and the one that is most used is called Cas9. Cas very creatively stands for CRISPR-associated protein. And then there are a bunch of Cases, and there are CFPs, and all sorts of things. It turns out that bacteria, surprise, there are a lot of them that have a lot of had 3 billion years to work at it, and they've come up with different ways of doing this. The protein then cuts the DNA at that spot, and it cuts both strands of it. And that incapacitates that. So if you just want to make that gene not work, that should be the trick. That's the cut part. So if there's a document that spells my name Greely, I could have it 1,000-word document, find every place where it's Greely and cut it out. But of course, I can also tell a word, replace it with Greely. And that's the third phase. The guy, which is the homing beacon, says, I'm going to find this. You've got the Cas9 or other Cases that then cut it. And you can put DNA that travel with it. That if you get lucky, if everything goes right, will go in and fit where you cut out the piece you didn't want. And so you find the piece that has the sickle cell version of the globin gene. You cut it out and you replace it with the one with the normal version. And maybe you just cured a really serious disease. The reason why scores of millions of dollars are being spent on patent is that billions of dollars, if not scores of billions of dollars, are being spent to try to figure out how to use this, mainly for human health. So the cut and paste, the cut and replace function is the inescapable metaphor for CRISPR. But I've got what I think is a really good analogy for CRISPR. CRISPR is the
Model T Ford. There were cars before the Model T. There were ways that humans were engineering DNA, editing DNA before CRISPR. Arguably, my Stanford colleague Paul Berg was the first one to do it, with a variety of postdocs and other collaborators, using moving genes from one organism into another through a process called recombinant DNA back in 1971. So, longer ago than many of you were alive, we were intentionally editing DNA. More recently, we've come up with other ways that are ZFNs, zinc finger nucleases. At least I know what the ZFN stands for. There's one called HeLas, which is another acronym. I don't have a clue what HeLa stands for. The good news for me is they're really good systems, but they're kind of made obsolete by CRISPR, so I don't have to worry about trying to figure out what HeLa stands for. The reason they have been made obsolete by CRISPR is the reason that other cars were made obsolete by the Model T. Before the Model T, cars were really expensive and broke down all the time. So you needed to have a lot of money, and you needed to be able to hire a chauffeur/mechanic who could drive it and keep it in running order. And for those of you who ever watched Downton Abbey, you needed to hope that he wouldn't be a charming Irishman who would run off with your daughter. Now, most people did not meet those criteria. There were cars in California before Henry Ford came out with the Model T in 1913. There were probably, I haven't been able to find the exact number, there were probably about 5,000. Once the Model T became available, it was cheap and it ran well, and anybody could drive it, more or less. Everybody could have a car, everybody has a car. There are 39 million people in California, and maybe 39 million. Getting up here today from Stanford, it felt like there were 39 million cars on Highway 280. There are lots of cars because they're cheap and they're easy and they work. CRISPR is revolutionary, not because it's the first time things have been done. It's revolutionary because it's cheaper, faster, easier, more accurate by 1 to 2 orders of magnitude. I remember when the fuss first began to be made about CRISPR, so they published in late June of 2012 in Science. It's about a year before the buzz really started about it. And I remember asking a Stanford colleague who's in the Bioscience lab, so have you done this CRISPR thing? He said, yeah. I said, so how was it? He said, well, it's a new tool. I figured my lab would need at least a month or 2 to really figure it out and start using it productively. So 2 hours. We got it working in the afternoon. They're high school kids who use CRISPR. So CRISPR is not perfect. It is a lot of people working on making it better. So you can't perfectly do everything you want with CRISPR yet, but we're going to get better and better at it. Gene drive. I mentioned gene drive. So gene drive is an extra trick with CRISPR, but it's a trick that only works in sexually reproducing organisms. So with bacteria, gene drive doesn't particularly help you. Take mosquitoes, which do sexually reproduce. Although we probably don't think about mosquito sex very much. If you put out a mutated mosquito, so it has 2 copies of a particular gene that say, don't bite humans, for example. You don't know that gene yet, that'll be a nice gene. When somebody discovers it, we don't have it. But assume it's got 2 copies of that, and it takes 2 copies in order for it not to bite mosquitoes, not bite humans. If it's got 1 bite and 1 not bite, it bites. So you release a gazillion of those into the environment. They don't bite. They have sex. All their offspring, though, they're all mating with 2 bite gene variants. So all of their offspring have 1 bite and 1 non-bite. They all bite. Of their offspring, it's the classic Mendelian 1-2-1. So a quarter of them have 2 not bites, a quarter of them have 2 bites, and half of them have 1 of each. And either it spreads or it doesn't, depending in part on whether there's an evolutionary advantage or an adaptive advantage or disadvantage to it, but it doesn't move fast. Here's what gene drive seems to do. Gene drive The parameters of what gene drive can and can't do are also uncertain, controversial. But if it works as its inventors expect, as it sometimes works at least in the lab, you get that mosquito with the 2 don't bite genes, and it mates with the mosquito with the 2 bite genes, and all the baby mosquitoes are 1 and 1, but all the baby mosquitoes inherit the CRISPR construct, which then changes their don't bite gene, their bite gene into a don't bite gene. And so it turns them into 2 don't bite genes. They have sex and have more baby mosquitoes that are bite, don't bite. The CRISPR construct stays around and changes them too. And depending on how long a generation takes and how big a population you're talking about, you could, in theory, change an entire huge population of a sexually reproducing species in 20 generations. Now, 20 generations for us is about 600 years. Long-term project. 20 generations for mosquitoes, a couple of years. You could, this has the possibility, at least, of changing the genes of every mosquito in the Western Hemisphere in the space of a few years. So that's an interesting add-on. Only works for sexually reproducing. What are we going to use this stuff for? People instantly jump to the sensible, reasonable uses for it. Things like making better crops, GM crops, in a very, very efficient way. It turns out that doing this with plants proved a little trickier than doing it with animals, but I think we'll fix that. People are already doing it with plants. It's a little harder. There's opposition to GM food, but you guys may or may not have noticed that it's been getting hot lately. And with climate change, it's probably going to be a lot easier to make crops more heat and drought resistant than it is to move the corn belt 200 miles north. And at some points, there is no farther 200 miles north to go for some of these crops. So I think we will clearly use it for agriculture, for livestock, and things like that. We will use it for other economic uses. We'll use it to try to make biofuels, to change algae so they produce nice fuel. We'll use it for bioremediation, to make bacteria that pick up heavy elements from the soil. And then you can harvest bacteria and make plants that pick it up differentially. Harvest them and you clean up the soil. Those are very sensible economic conventional uses. But we're humans. We'll use it for all sorts of stuff. That dog, is that a hypoallergenic dog or not? It is a hypoallergenic dog. So if you wanted to say a hypoallergenic Great Dane, CRISPR could probably give you that. Or it could give you a Great Dane that had that kind of fur and hair. Or it could give you roses. So anybody here grow roses? No one has successfully bred a blue rose. There's a Taiwanese group that bred kind of a lavenderish, very unsatisfying blue rose. We now have the whole genome of the common rose. Take some genes from, say, bluebells or other blue plants, move them in. Somebody's going to make a blue rose. Why? Because nobody's ever done it before. And it'll be cool. Some people will want it. Or a unicorn. I actually believe that in the next 20 years sometime, somebody's going to make a unicorn. Probably be a Silicon Valley billionaire with a 12-year-old daughter. Wants to make a unicorn for the 12-year-old daughter. There are actually 2 ways to do it. You could try to figure out the horn genes and move those into a colt embryo, horse, egg and sperm. Or you could take the buds, the embryonic cell buds that become horns in a horned animal and transplant them into a horse embryo. Somebody's going to do it, probably through CRISPR. Is there any good reason to do that? No. Is there any good reason not to do that? Well, that's another interesting question. Somebody's going to make a dragon. That's not going to fly, and it's probably not going to breathe fire. Although when I mentioned that to one scientist, he said, well, you know, this is what you might be, there's a very low temperature, volatile thing that you can, anyway, probably not going to breathe fire. Not going to, CRISPR doesn't repeal the laws of physics and chemistry. You get something that looks like a dragon. Maybe there's something with wings. They would But somebody's going to make a vaccine. Somebody, George Church would like to be the one, is going to make a woolly mammoth. Or a passenger pigeon. There were 3 to 5 billion passenger pigeons in eastern North America 150 years ago. The last passenger pigeon died 103 years ago. Why? Because we killed them. We shot hundreds of millions a year and sent them off to eat at restaurants, to eat at dog food, packs. We recklessly and maliciously murdered a species that had 3 to 5 billion members. It turns out that some of those members have been carefully preserved. Their DNA has been sequenced. There is a western pigeon, banded rock pigeon, banded bad-tail pigeon, that is genetically pretty similar to the passenger pigeon. You look to see the differences, and you start making edits. And at some point, when you think you're close enough, you try to turn that edited cell line, that's now kind of a passenger pigeon cell line, into pigeons. The extinction is likely to happen. People will do other things. They'll make glow-in-the-dark plants. There was actually already a go-go effort to make glow-in-the-dark plants that failed miserably, really embarrassingly. But they'll do it so they can line pathways with glow-in-the-dark plants. We'll do all sorts of weird things because that's what people do. We will also do some things that are what people do that are not so weird but not so nice. Smallpox, we think, exists in 2 labs. One at the CDC in Atlanta and one someplace in Russia. I've heard Moscow, but I've also heard other places. Some of us in this room will still have that nice little scar right up here. They always see the left arm, I think. It's about the size of a dime, pretty distinctive. From smallpox immunization. Many of you won't, because we stopped immunizing people for smallpox in about the 70s in the US. Most of the world, because there was no smallpox. It was finally driven extinct in the wild in the 90s. There's been no smallpox. Which means if smallpox gets out, then you guys are toast. Smallpox in populations that had no built-up immunity, like Western Hemisphere natives who met it when Columbus et al. Showed up with it, 80–90% mortality rates. Now we'll do better because of modern medicine, but what are we going to do when we've got 10 million people in the ICUs because they've got serious cases of smallpox? Happily, we trust that CDC, we hope that CDC and the Russians are going to protect it. But smallpox is one of many pox viruses. And there's mousepox, there's donkeypox, there's monkeypox, there's a bunch of poxes. We know their genomes. We know the smallpox genome. What's stopping somebody from getting a hold of, say, mousepox, looking at its genome, comparing it to the genome of smallpox, and starting to make edits with CRISPR? It's not the need for highly educated people in great labs, because high school kids can do this. I actually priced some of the equipment. If you buy it new, scores of thousands of dollars. If you buy it on eBay, you don't need the current, most up-to-date sequencer you're willing to spend to get a 5-year-old sequencer. They're cheap. $5 grand to get a lab. A garage and $5 grand. How are we going to stop that? So CRISPR is going to be used for good things. It's going to be used for silly things or frivolous things or things that, it's hard to say whether it's good or bad. And it's going to be used for, or at least we have to worry that it will be used for bad things as well. I've been talking about non-human uses. Here's the main reason I'm talking about non-human uses. Despite the fact that my next book is actually about Hui, or something close to that. My Mandarin is not very good. But this Chinese researcher who announced to the world last November that he had produced Nana and Lulu, the first 2 CRISPR babies. He did that. That was one of the most unethical, inappropriate, criminally reckless experiments I had ever heard of. It was wrong on at least 5 different levels. We can only hope that those little girls are going to be fine. But We don't know. And in fact, we know almost nothing about it because the Chinese government has decided that we don't need to know anything about it. And they would actually rather that we didn't know anything about it, except a little bit they want to tell us. Humans have been CRISPRed. Lots of humans we're trying to CRISPR right now in good ways. So go back to sickle cell. You can take a patient with sickle cell and change the cells in their bone marrow that make red blood cells, that change them from the sickle gene to the non-sickle gene. You might have a cure for a really nasty disease. Sickle cell, beta thalassemia, a whole bunch of single gene genetic diseases, there are about 6,000 of them, are at least in theory capable of being fixed by CRISPRing people. What freaks people out isn't so much CRISPRing people, it's CRISPRing people in a way that survives the person. So if you CRISPRed me to try to turn my hair brown again, and you didn't want to use Clairol or something, which would actually be the much more sensible route, those genes die with me. If, however, you CRISPR an embryo, all an embryo cells gets the new genes, including those special cells we call eggs and sperm, which means the next generation could inherit it, and the next generation, and the next generation, and the next generation. That's what all the fuss is about. I do have a 39,000-word article out in the online free download Journal of Law and Biosciences from about 10 days ago, that if you have trouble sleeping, I recommend it. I actually think it's pretty good. But I don't want to talk about the human side, in part because I think the human side is going to happen much more slowly, despite clear John Greely. Because we really care about human babies. You know, something that worked in 95 human babies and left the other 5 disabled is a disaster. Something that works in 95 calves and leaves the other 5 disabled, well, farmers will probably go with that. Something that works in 95 mosquitoes and leaves the other 5 mosquitoes disabled, people say, why couldn't you disable more of them? And we don't care nearly as much about non-humans. We're willing to take much bigger risks. And CRISPRing, germline CRISPRing, is and will remain for some significant period of time risky. Risks we will be willing to take with non-humans, but not willing to take with humans. So read my next book when it comes out sometime about the human side. But the non-human side, I think, is more pressing, in part because it's going to happen sooner. It's already happening now. In part because it's a lot harder to trace. We could have had people who've already CRISPRed mosquitoes in California, and how would we even know? Nobody's going around regularly genotyping or sequencing mosquitoes found in California. If they changed in the last year, how would we know? Maybe if they changed and turned fluorescent pink, we'd notice. But if they changed in some more subtle way, how would we know? So it's going to happen sooner. It's because the risk ratio is different, and it's going to be harder to catch. If you want to CRISPR human embryos, you need an IVF clinic. You need an obstetrician. You need an embryologist. You need a mother who's willing to risk her children's lives on this previously unused technique, or almost unused technique. All those things are going to slow it down compared to CRISPR mosquitoes. Which reminds me, I forgot one of the best uses, the mosquito use. We've been talking about mosquitoes, and I forgot to tell you about the great mosquito use, or tick use, or mouse use. So, and this is where gene drug comes in. Go back to the mosquitoes. 440,000 people die every year from malaria. 440,000. 22 million or so get a new case of malaria, which is extremely disabling for months and months, costs huge amounts of medical bills and lost work and so on, and it's extremely painful. People do not give people malaria. Mosquitoes give people malaria. Ironically, people give mosquitoes malaria. It's an endless cycle between us. What if we break the cycle? So one idea is to use CRISPR to get rid of mosquitoes. And the cleverest of these, I think, is to use CRISPR to make sure that all mosquitoes that get born are male. And if you do that enough, no more mosquitoes are going to get born. Right? Clever thought. But that has potential consequences for all the things that eat mosquitoes. And all the other things that get bit by mosquitoes, some of which we might like to have them get bit by mosquitoes because it keeps them from becoming nuisances in other ways. So what if we do this? Mosquitoes get infected with the malarial plasmodium because not only the mosquitoes have sex, but malaria has sex. But it's a really funky sexual cycle that requires it to mature through different forms, sometimes in mosquitoes and sometimes in humans and in different parts of humans. And so for a mosquito for a malarial plasmodium to reproduce, it has to be in a mosquito for a while, and it has to be in a human for a while. And it goes back into mosquito, and the infected mosquito gets bit, and the cycle starts over. What if we make mosquitoes immune to malaria? If they can't catch malaria, they can't give us malaria. And if they can't give us malaria, 440,000 kids, these are mainly kids, mainly in Africa, survive who don't survive. And if you use gene drive, you can force that through the population much more quickly. Even if there's some adaptive disadvantage to not carrying malaria, it's sort of hard to see. You'd still be able to force it through because the gene drive would be so powerful. So that's the other sort of public health use. Kevin Estell, one of the inventors of gene drive, wants to use it to deal with Lyme disease. We think of ticks and Lyme disease, and they're part of the cycle, but so are deer and so are mice. And so he wants to make mice that are immune to the spirochete that causes Lyme disease. And if you wipe it out in the mice, you wipe it out in people. So, another possible use of CRISPR. We've done the uses. I hope I've convinced you that the non-human stuff needs a lot of attention. Oh, and that's the other thing about the non-human stuff. It's not getting the attention. The oxygen's all sucked out by CRISPR babies. We are really myopic. We care so much about humans. We tend to forget that we're not the only life form on the planet. We are about 8% of the terrestrial mammals on the planet by mass, up from about 0.02% 10,000 years ago. But there are a lot of other organisms out here, and they affect the world in huge ways. And we're not paying enough attention. Which comes to my third main point. What should we do about it? Well, we should regulate, is one response. And the good news is we have regulation. The bad news is it sucks, basically. It was cobbled together in the mid-'80s to deal with GM food by a Reagan administration that A, didn't really know what it wanted to do, and B, was sure it couldn't get anything through Congress. So it took bills like the 1938 Federal Food, Drug, and Cosmetic Act, which of course was created with genetic engineering in mind. Wrong. And other things, the Federal Fungicide, Insecticide, and Rodenticide, Federal Insecticide, Fungicide, and Rodenticide Act, FIFRA, is my favorite federal act name. They took FIFRA and said, well, this applies to some of it, and this applies to some of it. And the result was a hodgepodge, a crazy quilt with lots of gaps. CRISPR showed the gaps. The U.S. Department of Agriculture has decided, well, it only has jurisdiction when you move a gene from one species to another. So if you're just cutting out a gene, they don't care. If you're just cutting out a gene and adding something that's not from another species, or modifying, editing it in a way that's not from another species, they don't care. So they refused the request by the creator to rule on a white button mushroom that when cut doesn't turn brown. They had knocked out a gene that makes the protein, the enzyme, that oxidizes the cut surface of the mushroom. Now, I'm not particularly worried about white button mushrooms that don't turn brown, but I'd still like somebody to take a look at it. USDA says it won't. On the other hand, the FDA says, if you're going to do anything with animals, that's a veterinary drug. And you have to go through phase 1, 2, and 3 trials and spend about $20 million before you can get it out. So you want to make your cat, you want to make some cats hypoallergenic? You got to spend $20 million to do it. Which I think is kind of crazy in the other direction. We have no consistent set of rules, and for things like microbes, we don't really have any rules at all at this point. Europe is a little clearer, they're against everything. This leads to another regulatory problem, though. Good luck enforcing it. If you need a Stanford or a Monsanto or a Salk Institute to do this stuff, we know where they live, right? We know how to find them. They've got regulatory compliance officers. They have skin in the game. They've got something to lose. they're going to pretty much obey the rules. If you've got two kids in a garage, A, how do you know they're there and what they're doing? And B, what do they care? They don't have $10 billion that you're going to find them. Even if you ever find out what they're doing, how are you going to enforce it? So the regulatory issues here are really tough on two levels. One is coming up with an appropriately, I think, risk-sensitive scheme that says, okay, these things make sense. For this one that's more dangerous, you have to do this. I think with gene drive, before you let a gene drive organism out into the environment, you really want a lot of effort. And sort of the equivalent of clinical trials is to take these things to an island someplace or inside a domed biosphere and check them out in something that's bigger than a petri dish, but small enough to be plausible. You want that. You want a really subtle, nuanced regulatory scheme. And I actually have such a scheme that I'm prepared to propose that has 7 parts. And the only part I haven't figured out is how in the world can I possibly imagine that Congress would pass a carefully thought through and nuanced regulatory scheme. The chance of that, even in normal political times, is close to 0. I don't blame the Reagan administration for not trying to pass new GM food legislation because it wouldn't have gotten through. Today, Congress can't agree on what 2 + 2 is. Half thinks it's 3 and half thinks it's 5. So how are we going to get good law? And if we get good law, let's say by a miracle, we get good law in the United States. What about Canada? You know those tricky Canadians. They're trying to keep all their cheap drugs to themselves, these greedy bastards. Or Trinidad and Tobago, or Somalia, or any place in the world. The Gates Foundation is funding some preliminary work about CRISPR mosquitoes in West Africa, which is where most of those 440,000 dead babies happen. They're in talks with a variety of the governments, particularly the government of Mali. Well, if you make CRISPR mosquitoes in Mali and release them in Mali, they don't know where the border is with Burkina Faso or Mauritania, and they don't care. So when one country does it, and it can affect all countries, how do you regulate that? Beats me. But this leads to my last point. I'm an optimist, except when I'm not. So I think we'll probably get a regulatory scheme. It's certainly not perfect, but we're actually, humans are pretty good at muddling through. I mean, we're still around and spreading like a plague. We muddle through okay. We've had 40 years of genetics, and we haven't had any big genetic disasters during that time. Ironically, the genetic disasters came earlier when we knew less about genetics and believed more in eugenics ideas. We muddle through okay. Let's assume we muddle through. This is the last point. How should we think about this? If, in fact, we have the tools and the desire to change the biosphere, what do we think about living in a garden or living in Disneyland? Living in a place where all the living organisms have been engineered by us, rather than living in a wilderness. Now, good news, bad news, there is no wilderness, and that every spot on Earth, including the lowermost reaches of the Marianas Trench, has been affected by the last 20,000 years of humans. We have changed everything. And are continuing to change everything, in part by having CO2 levels that are 50% higher than they were when I was born, which wasn't that long ago. I mean, a while ago, but it wasn't that long ago. We're changing everything, but still, to move from something that has major components that aren't under our control, and to the extent we're affecting them because we're idiots and we don't know what we're doing, to something where we've actually planned it out and designed it. I worked in Disneyland the summer before college, I was a dishwasher. I like Disneyland. Do I want to live at Disneyland? Do I want a world that's Disneyland? When I go to Yosemite, do I want to think, which has been dramatically changed by human intervention, including intervention by Native Americans before the Europeans got there in terms of the valley floor. But what do we want as a mix between what we have? We've changed the world enormously with agriculture, but now we can change it, the biosphere, in a much more fundamental way. There's reason to think we're going to do it. Should we do it? And how far? So, I came late, and ending with a little bit of time for questions. Usually I'm much better. I had like 0 time for questions. Basic questions. My answer is really easy. But I hope I've convinced you that this deserves attention. This, I think, is much more important than the John Creed and those 2 Chinese babies. This is something that can change the biosphere and will change the biosphere forever in ways that are good, bad, and just different. We need to start thinking about this and worrying about it yesterday. And I end with a charge. You, in this room, and 4 million that Rob tells me are watching online, now are among the world's, if you're like the 99.9999 percentile in terms of knowledge and awareness of this. With great knowledge comes great responsibility, to rip off Spider-Man, number 1. Pay attention to this stuff. Read about it, think about it, talk about it with people. It's important. Not enough people are paying attention. And I hope you guys will. Thanks for your attention. By the way, my email address is easy, hgreely@stanford.edu. Greely, L-Y, not L-E-Y. And I promise if you have a question that you can't ask me today and you want to send me an email, I promise to think about trying to answer.
So the floor is open, and Samir is going to be, people who ask online, feel free to ask, and Samir will be letting us know when there are questions there.
I have 2 questions, if I may indulge. One is, CRISPR really hit the media and the public attention recently. However, gene transfer gene therapy technology has been around for decades.
Well, first FDA approval came in 2017, but the research efforts have been around for a
The
long time.
science has been developed since.
Yeah, the first human trials were, I think, in 1980 or 81.
Right. So, if you look at the Gardner hype cycle.
Yep. I love the hype cycle.
The transfer gene therapies are already beyond, they're kind of in this maintenance thing. Now we're seeing more SMA, other gene therapies going to be approved. CRISPR is at that initial.
It's near the peak of the first wave of hype.
Right, and then we'll see this when the science gets refined, and then we'll see.
And then it'll either come back up if it works, as I think it will, or it'll peter out if it doesn't. So, there's the genome and the proteome and the metabolome, but the biggest of all of them is the hyperbolome. In bioscience, hype is king, and there is this great, really pretty descriptive hype cycle.
Right.
There's a sort of tamping down sine wave.
So, what do you think about all of the gene therapies that are not CRISPR, that are the better studied models,
Right.
and the impact of how that's going to change our species, really?
So if it's gene therapy for living people, sort of called somatic cells, it only changes your body cells and not your eggs and sperm. Apart from the fact that people are charging $2.1 million for a dose, and access issues and safety issues, I got no deep problem with that. That's medicine. Medicine has been changing our species forever. I would have been dead at least 4 times, but for medicine, I think probably most people in this room would have been dead at least once, but for modern medicine. So I don't have any problem with that. I actually think the germline stuff is less significant than people make it out to be. But I do think that we will see in the first gene therapies that are getting approved are not CRISPR therapies. There's zinc finger nucleases and penguins that have been worked on for a long time. And there are some other tricky things that people are doing. And I think those will get approved and they'll be used. And nobody's going to use it for new stuff because they're already CRISPR, probably. But that will add some positive experience with gene therapy, which may carry over inappropriately to the assessment of the early CRISPR trials. Basically, on safety, we need eternal vigilance. Actually, what was it? One of the big companies turns out cheated on some of the data they introduced about their gene therapy. Yeah, Novartis.
Novartis
Richard
of
bought
Texas.
that, right. And the FDA is not happy. The FDA needs to spank when people lie.
And sort of related, you said we should be very aware and very concerned about where we're doing this outside of the human species. And we can't ignore what's already going wrong, and how do we know, keep our eyes open.
Right.
So currently, and you brought this up in your lecture, the fertility clinics it's a cash cow, it's a multi-billion-dollar industry,
Yep.
and they're not regulated.
In most of the world they are. In the United
In the United
States,
States,
they
they're
will
not.
tell you they're incredibly regulated, and
They're really not
They're
regulated.
really not regulated.
And they're being funded by equity and hedge funds.
I
and
mean, that's
VCs.
relatively new. They've been a cash cow for the OBGYNs and the endocrinologists.
Right, but
and the
now
RIs.
there's real money interested in funding this because it's
It's
even
so
bigger
far
cash
down,
cow.
so maybe
But so one of my concerns is that whether it's gene transfer or gene editing by one of these enzyme nucleus systems, is parents who are desperate to have their own biological children do pre-genetic testing and find a mutation. I think that the opening for a desperate Silicon Valley billionaire parents who wants to CRISPR their embryo, that is possible now.
Sure.
And there's not in place any surveillance or regulation or any way to.
There is regulation that would be illegal in the United States and in most countries, but not in all countries, and catching it would be difficult. But I go back to the Model T. I'm not worried about 20 CRISPR babies. Unless there's 7.5 billion of us. And unless it becomes common, it's not really going to have much of an effect. And so, yeah, no regulatory system will prevent the occasional circumvention of it, but I'm not really in sleep over that. It probably will happen and we'll get huge headlines, but I don't think it will be fundamentally important. It's just a matter of numbers.
Do you think there are regulations preventing an IVF clinic from using CRISPR today?
Yes, it's illegal. Because the FDA has taken the position since Dolly the sheep that a genetically altered embryo is a drug or biological product. It might even be a medical device. I'm not quite sure on the device. But it's a drug or a biological product, and it's more than minimally manipulated human cells. And you can't sell that without FDA approval. You can't even do research on it without FDA giving you an investigative new drug exemption. And FDA needs some proof of safety before it's willing to do that in preclinical trials. And they're not going to grant any of those anytime soon, especially since Congress didn't trust FDA and put in the Appropriations Act each year for the last 4 years something saying FDA can't even grant an IND. This is kind of a funny story. Originally, that bill said FDA can't spend any money to consider an IND application. I kind of blame myself because I told some reporter, those morons. They don't even realize you turn in an IND application. If FDA doesn't block it within 30 days, it goes into effect. So if you tell them they can't spend any money on it, they can't spend any money to block it, so they all go into effect. So the new one says they can't spend any money on it, plus no such application for any heritable genetic modification, I think is the language, something close to that, will be deemed received. The 30 days goes from the date of receipt. So Congress has said, you get the Supreme Court to all swear. We saw him hand the IND to the receptionist. Doesn't count. Doesn't matter. So you can't even get an IND in the US, even if the FDA were inclined to grant it, which it isn't. So without FDA approval, it is illegal. Now, it's not. That is a misdemeanor, actually. But it's not a major criminal offense, but it is illegal. Yeah.
Follow up on that. What if there was no payment involved and somebody was doing it on themselves?
Yeah, self-experimentation. Here we are in the Bay Area with actually really kind of like Josiah Zahner, Mr. DIY Biology. He's injected himself with CRISPR. He's injected himself with vaccines. He's tried to sell glow-in-the-dark beer. It turns out not to work very well because you need to leave all the yeast on it, and the yeast goes to the bottom, and so you put it in a black light, you get a little bit of green at the bottom of the beer, not all that attractive. DIY is still covered by federal regulation. You're introducing it into interstate commerce whether you get paid or not. Getting paid is not the
Doing it
issue.
on yourself is a just
Yep.
commerce.
Yep. because some of the things that you use to make it will have moved to interstate commerce. So they nailed a stem cell clinic in Colorado. It was using only stem cells from patients in Colorado and doing all the work in Colorado and injecting them in Colorado. But not unusually, they were using antibiotics to treat some of the cell lines and keep them uncontaminated. And antibiotics came from outside Colorado. DC Circuit upheld that as an appropriate use of the commerce clause. Now, will FDA care about it? Probably not. If Josiah wants to, I kind of like Josiah, he's out there, but I hate to see him die a terrible death. If he wants to try, the FDA probably isn't going to work too hard to keep him from doing that. But if he starts publishing how-to manuals in great detail, I'd be able to believe that. Although there may be some First Amendment questions there. Yes?
Do you have a very brief summary of your 7-point nuance detail?
Yeah, brief summary. It's great.
So you should just repeat the question.
Yeah, so do I have a summary of my 7-point plan? And I have to remember whether they're actually 7. Everybody has to register. Everybody has to sign their work. You have to put a DNA sequence in anything you modify that is a unique registration sequence for you. And given 4 base pairs, like 10 base pairs is enough to make a million different registrations. 20 gets you to 1 trillion. So you can do that fairly easily. You have to give some advance notice to somebody. I don't really care whether it's a government agency or an independent nonprofit or something about what organisms you plan to work on and roughly what you want to do. And they can intervene in the extreme. If you say, I want to play around with smallpox, they can then go say, well, maybe not. Tell us more, etc. You need to use good laboratory practices to make sure that what you're doing in the lab doesn't escape. That's nothing new. Stanford, etc., know how to do that. Guys in garages maybe don't. Before you do any environmental release, you need to do the equivalent of a clinical trial. Or, no, it needs to be assessed for risks and then decide what you need to do. So there's a guy who wants to cure a hereditary disease, and I think it's in Dalmatians. And I'm not really worried about the Dalmatian thing getting out of control. They're dogs, they're pets. You're not going to have killer Dalmatians, these guys from Mississippi roaming the South. I wouldn't require a whole hell of a lot of safety, environmental safety information for them. You want to CRISPR mosquitoes? Yeah, I don't want safety information. You want to make release pet zoo or new improved pet zoo? Yeah, I'd like information on that. And the last one, which I think is the most important and often overlooked, I want a cleanup plan. I want to know that you got some ideas about what to do if things go wrong. Kevin Esfeld at MIT, to his credit, he vetted this thing, sort of pushed it and said, wait, there are some potential problems here. So he's worked a lot on ways to kill gene drive or cabin gene drive so it doesn't get out of control. People have talked about kill switches. You may remember from the first Jurassic Park, there was a kill switch that didn't work. But that was fiction. It didn't work. And the one thing you can always do is require insurance or bond or other things so that if people get hurt, there's some money to pay them off. So that's 6 points. I think that's it. I may have forgotten one. You were you.
Actually, so my question was you just answered.
Okay.
It was just going to be whether, given that things may go wrong, it can be created in the garage, stuff like that. What would be like the process to?
And how do you find people to force them to register? That's tricky, but unless they're really good, they're probably not going to create their own guide RNAs. They're going to buy them from somebody. And so you ask the companies that supply the guide RNAs to ask for and verify that somebody has a registration number on file. They're already looking for things like smallpox sequences. They've got a list of sequences that they want. So none of this is going to be perfect. It's sort of like drones. The FAA requires you to have a license for any drone over a ½ pound. Or people can buy drones in any place. They've gotten 500,000 licenses. People have sold millions of drones. It's pretty tough.
So I have a question, but I also had a follow-up on one of your points about the unique identifiers. Does
Yes.
that make it really easy to frame somebody?
Yeah. True.
I'm just
That-
gonna
I mean,
take
that-
Hank's sequence and put
Yeah,
it in this
true.
bioweapon.
Nothing's perfect.
Okay. So my
Yeah.
question is about
People have,
concerns.
when I was in college, my roommate, investigation of fake ID business. Always showing people to be 21. You had a big cutout, this is in the old days. And you hold it in front of your face with the whole picture, and then you laminate it. Iowa driver's license in theory. Stanford student. Moron. Misspelled license. So yeah, the idea is not going to be perfect.
So my question is about the level of concern among scientists who are using CRISPR about these non-human applications, and especially gene drive is my main concern. So, there's a ceremonial sort of summit of Jennifer Doudna and others who are using CRISPR to say, well, we're not going to go so far as to put a moratorium on research on sort of germline CRISPR, but we'll say that more evidence needs to be collected before we deem this safe. But what's their concern about all the non-human applications?
Not
gene
nearly
drive?
enough.
Are there any CRISPR folks who are talking about
Kevin,
this?
that's so.
Cool.
Who's the gene drive inventor? There are a few people who are concerned, but so I actually gotten to know Jennifer and liked her quite a lot. She had a dream. She says where she got concerned about unethical uses. She had a dream where one of her friends, Deane and Carol, back in Utah, said, he had this friend who wanted to hear her talk about CRISPR. Would she explain it to him? Then she thought the guy was facing away from her, which she thought was weird. So she goes through the whole CRISPR explanation. And he turns around, and it's Hitler, but with a pig sound. I don't know. Dreams. I don't know where the pig sound came from. And she woke up in a cold sweat. And one of the things she did was call a meeting in Napa in the last weekend in January 25th. Yeah, 2015. And they invited about 14 people, and I was lucky enough to be one of them. And there were two lawyers, me and Aldo Charlotte from the University of Wisconsin. And we both pushed for dealing with non-humans. It's important. Nobody else wanted to do it. They all wanted to do humans. This was really a provocative meeting. A paper in Science came out of it. The authors listed alphabetically. And just by chance, alphabetically, the first two authors were David Baltimore and Paul Berg, two Nobel Prize winners who have also been two of the 5 members of the committee that had organized the famous Silmar Conference almost exactly 40 years before. And they said, we promised people we wouldn't do germline, and now people are going to do germline, that's what we need to worry about. Well, they couldn't actually produce where they promised it or how they had the power to promise all of science not doing it. But Alton and I tried, but we couldn't get focus. Alton and I actually have a paper in a job in the American Journal of Bioethics called CRISPR Critters, and CRISPR Cracks, where we tried to make this argument more. I don't think enough attention is being paid to it, and it's in part because we are, not remarkably, I suppose mosquitoes maybe think mosquitoes is a height of all creation, but we're a really vain species. We don't really care about ourselves, with the exception of the occasional longer or panda. Any questions online? No. Send them all off. Yeah.
Yeah, so going back to regulation, we can see that companies and universities are likely to follow the regulations because they have things to lose. But
More or less.
yeah, what about the people in their garages,
Yeah, it's a problem.
Um,
We can threaten them with jail. Although, I'm informed and believe on the basis alleged that 20-year-old guys sometimes do things that
yeah, perhaps they require the help of some other companies to make the reagents, right? But the cost of producing small nucleotide sequences is dropping dramatically.
Yeah.
And
Once they make their own guide RNAs, it's going to be a really hard.
yeah, all the reagents are going to be so cheap and accessible to everyone, high schoolers.
Yeah.
So how do we regulate them?
As best we can.
All right.
We ask people, we tell them there's swinging fines. We have all the bits of the ecosystem. You buy a piece of equipment off eBay that would be used for this, and somebody notes that it was shipped to this address. And maybe if they then see that something else, a reagent that and it's tricky and it's expensive, and I don't know whether we'll do it until there's a disaster. What? Legislation comes for two basic reasons. People work, they see a problem and they work for years and years to get all the interest groups aligned, and everybody finally agrees, and then the politics work out, and the Genetic Information Non-Discrimination Act after 13 years finally gets passed. When the insurance companies are okay with it, and employers are okay with it, and consumer groups are okay with it, you get a Democratic House of Representatives that passes it. The other thing is like the USA Patriot Act, the world's worst acronym, by the way. That's an acronym. It's like a 17-word title to the act. Something bad happens, and people use it to say, don't just stand there and pass something. And so they pick every idea that's been out there, good, bad, or different, and stick it into a bill. The actual thing, the actual cure to what truly happened in 9/11 was implemented almost immediately by barring the cabin doors and basically not allowing anybody to get into the cockpit. And in a sad way, that plane that crashed in Pennsylvania was a cure for that by crashing there rather than crashing into where it was supposed to crash into. So disasters have a way of producing law. FDA, everything important in the FDA came about as a result of some sort of scandal. Usually dead people, often dead babies. So my best hope is come up with a good suite that's discussed widely and generally acceptable, and have it ready for when the disaster hits.
Yes, sort of a thought though. Yes, I mean, embedded in a lot of these comments. Yeah, we have to. Embedded though in a lot of these assumptions or sort of statements, or at least somewhat embedded, is somebody with power on high will need to control the situation. I think perhaps one way to think about it is because these technologies are so robust. You know, like lots of people have weather stations on their house now. Look how we do weather. So we could be doing biological surveillance, kind of like the same way we do weather now. Like maybe it's going to be a crowdsourcing type of activity that makes it go.
Yeah, I always like that. I think that you touched on a really important point, in that monitoring is crucial, and we always underinvest in monitoring. Like universities can get people to give hundreds of millions of dollars to build new buildings, but they can't get anybody to give money to keep them up, make the air conditioning work, and pay the janitors. Monitoring and continued monitoring and surveillance is essential to making this stuff work. We don't have anything that's regularly monitoring it. The idea, I love that. Will be acknowledged in the footnote. The idea of crowdsourcing the monitoring, because I think there would be people who would find it cool. Let's catch, gosh, is this year's mosquito the same as last year's mosquito in my backyard? Or, since I can't tell mosquito species apart, how many different mosquito species were biting me last night? And managed to swat. I can see that happening. And again, as prices fall for sequencing or genotyping, that would be a really good use of it for do-it-yourself community. Thank you.
So we're looking forward to your next book with John Quay about him. Do you any sneak preview or what? Lots to be said about him.
It was a really, really, really bad experiment. And there are some lessons we should learn and some things we should do, including not overreact. But he should never work with the act. Both to punish him, but more importantly to deter other people. He thought he was going to be famous. Other people know that doing this doesn't make you famous. It gets you locked into a Chinese prison for who knows how long or something. We need a system of snitching. At least 8 academics, including 3 of my colleagues at Stanford, knew that he was either doing it or planning to do it. Nobody told anybody. Now, I don't really blame them. For one thing, snitching is not generally approved. For another, it's science confidential. Somebody asks you to keep their results and work confidential. That's a powerful motive. But the third one, which I think we could work on, is one of them, Matt Porteous at Stanford, said, in retrospect, I wish I had told somebody, but who would I have told? Who could I go to? Should I try to find the IRB at Chinese Southern University in China in Shenzhen? So I think we need to set up set the goal that if you see grossly unethical research, you should feel a duty to report it, and a mechanism that makes it easier to report it. And then the third thing, science needs to be a little more humble. The early reports said safety, efficacy, good cases, and the original one was global consensus in favor. The global consensus in favor is crazy because there's not a global consensus on what 2 + 2 is. But some sort of general approval or acceptance and recognition that this is not the scientist's call. The public has a right to be heard. And in the last go-round, that's kind of dropped out. It's, well, this is coming and we need to set out the steps that need to be followed before we're confident that it's safe enough to be used. But the we there is implicitly the scientists. And science cannot and should not, but more importantly, cannot be divorced from its society. And so I think science needs to be a little more humble about recognizing that even things that science thinks are dumb, if the country doesn't want to do it, or wants to do it, they're in charge or not. For better and for worse.
On that note, please join me in thanking Hank Greeley for This is a reminder, we have Dr. Amrit Ray, who's the Global President of Pfizer, speaking on October 26th.
10.
October 10th. So we hope you'll join us for that and other events. And thank you so much. And please help yourself to refreshments. And if you have other questions, maybe Professor Greely will be around for a little bit. Okay, all right. But if not, we have his email. Okay, thank you all for coming, and thank you those of you online for joining us as well.